Hello and welcome back. Example 7 says find the centroid of a region enclosed by y equals x and y equals x squared. And I've taken the liberty to draw a quick sketch of y equals x and y equals x squared. Now they intersect in 2 points, x equals 0 and x equals 1. And so the region that's pinched off is that little region in the first quadrant between 0 and 1, both in x and y direction. So here we have y equals x on the top and then y equals x squared on the bottom. Now we're going to take that region and break it up into a bunch of strips, a bunch of vertical rectangles that we'll use. We actually have a choice about whether or not we want to use vertical rectangles or horizontal. Well, since we have both of the functions written as y equals those functions, it'll be easy to get the height of the strips because we'll take the top y value minus the bottom y value. We're going to need to do that in just a second. But say we have our strip at some given x value. Again, this is like an infinitely thin version of the strip. We'll put a little dot right there to represent the center of mass of that strip. So this is our x tilde, y tilde. We can get the x tilde by just writing x. That's the center of mass in the x direction, is just x, because remember this is infinitely thin, this rectangle. And then to get the y tilde, the center of mass in the y direction, we're just going to take the average of the top y value and the bottom y value to get like the midpoint, right? Top y value plus the bottom y value divided by 2. So let's do that here. What I'm going to do is write, we're going to take the top plus the bottom divided by 2. And in that case, you get the top function. Let me just write out where the top function is. That's going to be y equals x. The bottom function is y equals x squared. So we'll have x plus x squared divided by 2. So that's the center of mass of each strip. Now the area of each strip, dA, we can get by taking the length of the strip, or the height of the strip, you could say, which is going to be the top y value minus the bottom y value. So the top y value here minus the bottom y value, that'll be x minus x squared. Times the width of the rectangle, which is going to be dx, an infinitely thin width. So if we wanted to write here, we did top minus bottom to get the height of the rectangle. All right, we have everything that we need now to start getting our integrals set up. Okay, so the first thing we'll find is A, which is the area of that region. So that's going to be the integral from 0 to 1 of the top function minus the bottom function. This goes way back to like section 6.1, where we're trying to find the area between two curves. Just take the top function minus the bottom function, and there we go. So when we evaluate this integral, you end up getting something like 1/6. Now to find x bar, which is the x coordinate of the center of mass, we're going to take 1 over that area, 1 over 1/6, times the integral across our region from 0 to 1. Again, these are x equals 0 to x equals 1 across the region because we're making our strips vertical like this, just like before. If you have vertical strips, you're going to be integrating with respect to x. Horizontal strips, you're integrating with respect to y. So from 0 to 1, x tilde, which is x, and then times dA, which is x minus x squared times dx. So let me just highlight what these are. So this is x tilde, and this is, this is dA. And once again, you can find this integral. It takes a few steps, distribute the x, and then integrate term by term. And eventually, you should get 1/2. So then we have y bar, which is 1 over the area, 1 over a, times the integral from 0 to 1. It's still in terms of x. Even to find y bar, we're still integrating in terms of x. But now it's going to be y tilde, which is this whole x plus x squared over 2 thing. That's what y tilde was. Y tilde was x plus x2, x plus x squared all over 2. And then times dA, which is the same x minus x squared dx. Slightly more complicated integral, but just kind of take them as you get them. There's your y tilde and your dA. So if we work that one out, you get 2/5, turns out. So our centroid, center of mass, assuming that we have constant area density spread throughout, is 1/2, 2/5. So that's about like right here. So here's about 1/2, and then 2/5 is maybe right there. So it's somewhere right around there. It's actually almost where we drew that dot. Okay. So there's example 7. We'll move on to example 8, which says find the centroid of the region by x equals y squared minus y, and then x equals y. I think that should actually read between those two. Let's draw a picture of those parabolas. And so what we're going to do is first find the intersection points. So let me find the intersection points. Oops. Okay, give me one quick. Okay, so we're finding the intersection points between these two curves. So what we'll do is we'll set these curves equal to each other. We have y squared minus y equals y. We'll subtract the y over. It's tempting to want to divide through by y, but then you're going to lose the solution y equals 0. Factor out the y, and you'll get y equals 0 and y equals 2. So let's draw a little picture of what's going on here. Okay, oops. So here we've got y equals 0. If you have y equals 0, that will correspond with x equals 0 for both of these curves. And then when you plug in y equals 2, and actually let me just write a scale. So we have y equals 2 in there. And knowing the x scale, I'll just draw that in there as well. When y equals 2, we're going to have x equals 2 for both of these as well. So there's another point of intersection. Now if we look at the second curve, it's x equals y. That's just a line. And if we look at the first curve, we have x equals y squared minus y. That's a parabola that's opening to the right. Now if the parabola is going to intersect those 2 points, then it's going to look something like this. It's going to look something like that, opening to the right. So it'll intersect 0, 0, and 2, 2, and open to the right. So there's a little region there. I don't know what the x value is of that vertex, but we don't really need to find that out in this case. Now here we have a choice. We can either make our rectangles vertical like we have in the past, or we can make them horizontal. Now vertical is not a very good choice here because the top and the bottom curve are changing formulas, right? Right here at x equals 0, it's changing from having the parabola on both top and bottom to having the parabola on top and the line on the bottom. So vertical rectangles are not looking too good as a choice. Maybe we can try horizontal rectangles, and it looks like that's going to work much better because not only are we going to have the same curve on the right side and the left side over our entire region, but we also have our functions, or these curves, expressed as x in terms of y. So we'll be able to get the x value of this right side curve and then the x value of the left side curve. So horizontal rectangles it is. Remember, our rectangles are infinitely thin too, but we're drawing them with a little bit of thickness just to draw them like that. So here's a rectangle at y, just some random y value. Let's figure out the, make a little bit of space for that. Let's figure out what the x tilde y tilde is. Now in this case, x tilde is going to be the midpoint of the right and the left x values of these two curves. And I'm going to label those. The right curve is x equals y. The left curve is x equals y squared minus y. So x tilde is going to be the average of those two x values, right? That's going to give you the x value that's in between those two x values. Take their average. So we're going to have y. We'll have y. Oops. Plus y squared minus y over 2. Then y tilde is just going to be y, right? These are infinitely thin rectangles, so the center of mass of those rectangles, y tilde, will just be the y value of the rectangle, of the infinitely thin rectangle. So we can simplify this to just y squared over 2 comma y. Now the other thing we have to find is dA, which is the area of one of those infinitely thin rectangles. And for that, we're going to do the length of this rectangle, which is the right x value minus the left x value. This is going to be y minus y squared minus y. And then times dy. So just to label these things, the x tilde we got from doing right plus left divided by 2, the average of the right and the left x values. dA we got from doing right minus left. Now we could simplify a little bit because we have a y minus negative y, so that's going to be 2y minus y squared dy. So there's our dA. Okay. So now we can find the area by integrating over our region. Now we're going to do this with respect to y from the bottom to the top. So from y equals 0 to y equals 2. And here we mentioned you can think about it as like the right x value minus the left x value, or you can just integrate dA. We already kind of went through that thought process of right minus left. So we're just going to integrate dA to give us the area of the region. So here, if you work this out, you'll get 4 over 3. Then x bar, the x coordinate of the centroid, is going to be 1 over that area times the integral from y equals 0 to y equals 2 across our region of x tilde dA. So x tilde was y squared over 2, and then dA was 2y minus y squared dy. Again, you can work that out. In this case, you'll get 3/5. Then we have y bar, which is 1 over the area, times the integral from 0 to 2 of now y tilde, which we said was y, and then dA, which is the 2y minus y squared dy. Again, work that one out, and you get something like 1. Well, you get exactly 1. So the center of mass, or more specifically the centroid, which says that our area density is constant throughout, is 3/5, 1. 3/5, 1. We can just do a quick check to make sure that that sounds reasonable. 3/5, 1, that's right around here. So that seems pretty reasonable. One last aside that I'll mention is that the center of mass doesn't necessarily have to be in your region. Now most of the time it will be, but I'll just sketch up a quick picture of some object where the center of mass is not in the middle of the region. So I've drawn like a upside down or a horseshoe, and the center of mass of the horseshoe, if you've ever tried to balance a horseshoe so that it's kind of flat, it just doesn't work because there's not really a good balancing point. I mean, you could make it so that it was pointing down, but if you tried to make it so it was sticking out, so it was horizontally flat, there's not really a good balancing point, because the balancing point is going to be somewhere outside of that horseshoe region. So that could happen. The center of mass could be outside of the region. All right, well, thank you very much for watching, and see you in the next video.